Hi, welcome to my walkthrough of the AQA GCSE Computer Science Paper 1 exam from May 2018. I'll also be doing the equivalent video for Paper 2 of this exam series, and also I've already done walkthroughs of the two sample papers, so you may want to see those as well. The way these work is I go through and answer the questions as if I was doing it myself, but of course I'll be explaining bits and pieces as we go along. I'm not going to be explaining stuff in the full amount of detail in all cases, and also, exams don't cover the entirety of the specifications, so it's really important you know the content, and I have got videos which cover all of that content in its kind of lesson form, so there'll be a link in the description to that playlist. I'd recommend you watch that if you're not up to speed on the content for this paper. Because I'm effectively going to be showing you the answers, I do feel the need to recommend you try this paper yourself under exam conditions. As I record this, you're not blessed with many papers, you've only got the sample paper and this paper for this component, so you need to make the most of those two. Knowing the answers before you do a mock or before you try it yourself isn't going to be helpful, so try it yourself. If you don't have access to this PDF, you could maybe ask your teacher, or also just pause this video as I go through it so you can see the questions and then pause it before I give you the answers, and then you can mark it based on my answers. So that's how I would suggest you do it. Of course it's up to you, but that would be my strong recommendation. Let's have a look at this front page then before we begin. So first of all, the name of this paper or this component is computational thinking and problem solving. So out of the two components, this is the more practical based problem solving type paper. The second one is about theoretical recall essentially, but that doesn't mean you don't have to revise for this. There is a lot of theory and we'll encounter that as we go through it. So some people will turn up to this exam not having done much revision because they figure that they're good at programming, they're good at thinking on their feet, they're going to be fine. But actually there is a lot of recall, a lot of theory you've got to have learnt to be able to do well at this paper. This is an hour and a half long, so kind of an average length paper, and it's out of 80 marks. So most teachers advise you to do a minute a mark. So an hour and 30 minutes is 90 minutes. It's out of 80, so if you do a minute a mark, you dedicate a minute to each mark a question's worth, you have 10 minutes spare at the end. That's a really good technique to use, but don't always take it so seriously, because some questions you're going to race through and other questions might be only 1 mark, but it might take you a couple of minutes to do. So it's not an exact science, but it's a good guide to go on, and it is really useful to check your answers at the end, so you need a bit of time to do that as well. On the subject of marks, here are the grade boundaries from this exam series. We've got the two computer science ones here out of 80 marks each, and we can see that for paper 1, to get a 9, which is obviously the top grade, you needed 72 marks out of 80. So only 8 marks you can drop, that's 90%. So it's really tight, there's not much room for error here, unfortunately, and it's useful to have this context. Obviously I hope everyone's aiming for a 9, but it's obviously perfectly fine to get lower than a 9. That's perfect, these are good grades as well. So it's useful to know roughly what you need to get for each of these, because it's going to be similar for your exam. I'm always asked to predict grade boundaries, and you can't, because they're actually calculated after everyone has had their exams marked. So if the exam board don't know in advance what these are going to be, they basically look at the data and make sure it's a nice bell curve so that it's standardized, and they'll adjust it based on how difficult or easy the paper is. So they can't be predicted, but they are going to be similar to these ones, and generally speaking they do rise year on year because people have access to more past papers, more resources become available, teachers get more used to teaching the specifications, so people get better at it, hence they tend to rise year on year to keep things nice and fair. But it's not going to rise by a huge amount. If it does rise, it will be 1 or 2 marks, but we haven't got too much room here for any increases. So useful to know this stuff, but don't focus on it too much. I don't want anyone panicking in the exam because there's a 7 mark question they can't answer and they suddenly think that the 9 is gone. You'll get what you get, it doesn't matter too much, which is easy for me to say, but it's not worth worrying about too much. Going back to the actual paper, so you can't use a calculator for this, that's important. For maths will be quite easy. Also basic things like having to use black ink. Don't use blue because they scan these and it might not show up very well. And I really emphasise that because this day here is quite significant, because this is the first date of GCSE exams, and because this is a morning paper, it's the first ever exam this cohort sat, and it's also the first exam for 2019 cohort will sit, and possibly beyond that as well. The timetables for beyond 2019 haven't been released yet, but it's possible that this exam will also be the first for the future students as well. So because of the significance of this date, I feel like I should give a bit more advice. So apologies if it doesn't apply to you. Some of you may be 2 years away from doing your actual GCSE. Some of you may not be doing a GCSE. So for those which are, and maybe for people who are watching just before their exam, because this is the first one, it's very, very normal to be extra nervous or extra anxious. The way you're feeling ahead of this exam is not necessarily how you're going to feel ahead of your other exams, because clearly the first one, there's a lot more uncertainty and you may not have sat a real exam before, so you're going to feel you're going to have a heightened state of emotion before this one. So it's really important to first of all be kind to yourself, because it's normal to feel that way. Don't feel bad because you're feeling bad about it. If you are, some of you may be feeling perfectly confident, which is fantastic, but also try and give yourself the best chance. You want to start off in a good way and sort of build the momentum as you go through all the exams. So you want to start off well, so try and do as much revision and try and do it in advance of this date, because for me personally, this may not apply to everyone, I just couldn't revise before my first exam singular really, because I would just have a bit of a block for a few days before this. I'm not sure why exactly, possibly because I didn't want to really focus on it. I was trying to, I guess, put myself in a happy place and try and avoid the inevitability of having to sit this exam in a few days' time. So do the work as early as possible if it is possible. Some of you may be watching this just before. It's also never too late to start revising, so my videos which cover all the content only take a couple of hours to watch, which is no time at all if you consider that it maybe took you 2 years to get to this point. Also make sure you get the basics right for this. Start as you mean to go on, essentially. So the basics being things like making sure you get enough sleep, or trying to get enough sleep. Don't spend all night revising. Make sure you have breakfast, make sure you have enough food, enough water to get you through this. It's a 9 AM exam, you need energy to get you past that, a coffee if you need to. Also make sure you get to the exam on time. Don't cause yourself stress by leaving things to the last minute. It's better to be early than to turn up a little bit late or just on time, because that'll make you more anxious, potentially, more stressed at least. One of the issues I had, which I wish was unique to me, but I'm sure applies to a lot of people as well, is just not being able to sleep the night before a big exam, especially the first one. So it's really important you try and get your good night's sleep, i.e. you go to bed so you've got 8 hours before you have to wake up, or whatever amount of time you need. But if you can't sleep, if you're lying in bed at 4 in the morning, staring at the ceiling and starting to worry about, turning up the next day and just not being able to do very well because you're tired, that isn't an issue. You'll be able to get through it. Your body can survive on not much sleep. You're not doing a hugely intensive thing. You're not running a marathon. You can survive on not much energy. The adrenaline will get you through it. That's perfectly fine. So try not to panic if you just can't sleep. It's not a big deal, but it's definitely preferable to be lying in bed and just not being able to sleep rather than staying up to revise all night and not sleeping that way. Try and sleep, but don't worry about it too much. It's a good time to just try and clear your mind as much as you can. So that's my general advice. It's also worth pointing out that paper 2 is on the Thursday afternoon as it stands. So I'll talk more about that in the paper 2 video and the consequences of that. So I'll leave that until then. But generally speaking, if you're watching this maybe a few weeks or a few months before your exam, I have got a video on how to revise computer science. So that'll be linked in the description. I talk through the actual methods you can do to learn all this content. Okay, let's begin, because that was a very long introduction. So first of all, we need to start by defining the term algorithm for 2 marks. So this is a pretty standard definition which you can express in various ways, but essentially an algorithm is there to solve a problem, and the way we do this is by specifying a sequence of instructions. So let's just say it's a sequence of instructions which solve a problem when they are followed. The idea being that it doesn't matter who follows the instructions. It could be a computer, it could be a human, but you're going to end up having solved this problem just by following these sequence of instructions. So exam technique wise, 2 marks, we've kind of got 1 point here, sequence of instructions, and the other half is about solving a problem. So it's useful to think of your answers in terms of how the examiner is going to be marking them based on kind of like a mark scheme with bullet points. Right, next we've got some terms labelled A to E. So we've got abstraction, data type, decomposition, efficiency and input. And we've got definitions in a table. We need to assign the label which matches up to the definitions. The first one is breaking a problem down into a number of sub-problems. So this is decomposition. You can probably get that just by looking at the term. Decomposition in nature is breaking things down. So here we're breaking things down into sub-problems. So we start off with a big problem, and we're trying to separate it into individual units which we can solve independently. That's what decomposition is, and it's a technique for solving problems. The next definition is the process of removing unnecessary detail from a problem. Again, another problem-solving technique, and this is abstraction. So they're not the same. People often think they're kind of like a couple, so they're opposites of each other, but they are different, even if they do seem similar. So abstraction is about removing detail from a problem, simplifying it really. So if they were being used together, you can maybe say, okay, well, we're going to abstract this problem, whatever it is, by decomposing it and then maybe removing part of it. So maybe we say, okay, this is less important, this is the most important sub-problem. We're then kind of using both of these techniques in one go. Both of their premises are really about simplification, i.e. that it's easier to solve a problem the more simple it is. And the final definition is defines the range of values a variable may take. So this is going to be B, data type. It's maybe not as obvious. Well, I think by power of deduction you could figure out that it's going to be B. But data type is about classifying different types of data, hence the name. So we have, I think, 5 basic ones which are in every single language. So we have integer, we have real for like 0.5, integers, whole numbers. We have Boolean, string, character, date, time, and that's for sort of 5 primitive ones. Then every language has their own ones, and they all have kind of specific things about them. So they're kind of set rules, because we can look at a number, we can look at maybe 5 plus 5 and see instinctively that these are numbers. This is going to be 10. The computer needs to know whether these are numbers or they are characters, because a 5 could be a character. So it needs to have this kind of distinction, and we often manifest itself when we're dealing with variables. So we often will write something like int counter equals 5 to tell the programming language that this is going to be an integer. It can only do, mathematical operations. You can't do like substring. You can't do string operations on this integer, and it's got to be a whole number. So we've got to actually tell the computer that we're dealing with data in this way, and this includes the actual range of values. So for integers, it might be hypothetically like -1 million to +1 million. That might be a range of values that an integer can take. And there might be another version which is -10 million. It's slightly bigger. So this is all included in actually classifying this data. So that's just part of what a data type does. And in some languages, this is done more behind the scenes. So in Python, we don't actually ever really have to specify the data type. It's already, it's being done behind the scenes. But in other languages, we have to be more explicit. But we still have to be really precise when we're dealing with programming languages, which is why we have to specify a range of values when we're dealing with data types. Next up, we've got some pseudocode for this algorithm which has been developed to automate the quantity of dog biscuits to put in a dog bowl at certain times of the day, and it contains an error apparently. So first of all, we need to shade one lozenge which shows the line number where selection is first used in this. So we have 3 basic constructs. We have selection, and we also have iteration, or repetition, iteration, and also sequence. So iteration is a loop, sequence is just going line by line, and selection is about going in multiple execution paths based on some condition or some selection really. So first of all, we've got if blocks, and that's what selection is, if and else. So if the time equals breakfast, then we're going to do something. If not, we're going to do something else. That's about going multiple execution paths. So it first appears in line 2. So there you go. I'm pretty sure these are marked by a computer, so you've got to be a little bit careful how you shade this. Do it more neatly than I have there. But next up, we have, going down here, another multiple choice. So we need to, I should probably read ahead. Now we're looking at iteration. So as I was saying, the loop. So let's go back up. So where's our first loop? Our first loop is down here. We've got a for loop, so this occurs on line 11. Now I need to shade the lozenge which shows how many times this subroutine dispense biscuit would be called if the user input is breakfast. So a subroutine call is where we reference it outside of where it's been defined. So that's how we actually use it in our main body of code. Usually they are defined right at the top of code, because the whole point is we can repeat them. So this is its, as my thing loads again, so we've got it referenced here, and we need to say how many times it would be called if breakfast is the input. So if time equals breakfast, then q equals 1, and we jump down here, and then for n to 1 to q, so we start off with n being 1, and we keep going until it's q. Well, q is 1 in this case because that's what our input has been. And if n is less than 3, then we dispense biscuit, and this only happens once because q is our upper limit. So we start off with 1, we're going to stop when it ends up with 1. Well, we do it at least once, so it's going to be used once because n is less than 3 in this case. And finally, or maybe not finally, we've now got to show this type of a variable time in the algorithm. So we can probably have a guess of what this is going to be, but it's worth just checking. So actually no, I was going to guess it was a number, but actually it's a user input. So a user input is a string, and we can tell that because we've got quotes around this comparison. There's no point comparing it if this was an integer, but anyway, user input is often, it's almost always a string. So it's going to be a string in this case. That's our data type. Now we need to actually state ourselves how many times this subroutine will be called with the parameter chewies if the user input is lunch. So before it was just asking us about it being called in general, but now we're looking for this particular parameter being supplied. So a parameter is like a variable which is used or can be used by a subroutine. So we're not looking at in terms of the parameter being crunchy, just for chewies, and with lunch as our input. So in this case, q equals 4, so our upper range of this loop is 4, and we start off with 1, and it's going to go from 1 to 4, so it's going to loop 4 times. 3 of those times are going to be less than, 2 of those times are going to be less than 3 because the only numbers less than 3 in this range are 1 and 2. So this is only going to get executed twice. It's going to be called twice with this, despite having an extra loop that goes to this else statement. So this is times 2. You've got to be really careful with the less than signs. I almost fell into the trap of messing it up, but only 0 and 1 are less than 2. 2 is not included. If it was a less than or equal to sign, obviously 2 would be included in that range as well. Next, we need to state how many possible values the result of this comparison time equals dinner could have in the algorithm. So here this is a comparison as it tells us, but often you'll see the 2 equal sign as the comparison. This is pseudocode. They can kind of do what they want as long as we understand what's going on. That's perfectly fine. I would personally use 2 equal signs, and I use equals as a variable. They use a little arrow as a variable assignment, but that's not really relevant here. I just thought I'd mention it. So we've got this comparison, and a comparison is doing one of 2 things. It's either saying, okay, this is true, dinner does equal time, or it's saying it's false, dinner does not equal time. So there's only 2 possible values here, the 2 Boolean values. So again, the answer is twice. So again, the answer is not twice, the answer is 2 times. The 2 possible values. And these values are going to be either true or false. As it mentioned right at the start, there is an error in this, so we need to state the line number where the error has been made. The only real way to do this, apart from just staring at it, is to go top to bottom and see if you can spot any mistakes or inconsistencies or anything like that. So first of all, the input is fine. We've got breakfast and lunch, and we're assigning values to Q in this case. I'm not sure what the values mean. It's kind of particular to this dog food, dog biscuits. Dinner, it's the same. We've got the same kind of comparison line, and now we're doing 2 assigned to A. Well, actually you can see here that A is different to Q. Q's been used here in both cases, but A is suddenly used here. A doesn't really come from anywhere, and it's also not used anywhere else in this code. So it's possible this is just a mistype. They're meant to do Q and typed A. It's possible that this A is used in another part of this program and they've just used it here by mistake, but it doesn't follow the pattern, so we can safely assume this is a logic error. So this was in line 7, and now we need to write one line of code which would correct the error found in this. And so it's currently A equals 2, and we want it to be Q equals 2. Question 3 begins with us being shown a bit pattern which represents a binary number. Of course, everything is represented by binaries, so this bit pattern could be representing a very small image or a character, but in this case we're told it's a number. So we need to say what is the result of applying a left binary shift of 2 to this bit pattern. We need to express this as a bit pattern. It's only 1 mark, so they're not very generous often with these binary questions because it's seen as being very easy. So binary shifts are all about adding zeros, and the end you add zeros to depends on which direction. So a left shift is about moving this number to the left, and the way we do this is by adding zeros in from the right, and vice versa. A right shift is about moving the other way, and we add in zeros from the left. So here we're doing 2 of these operations. So first of all, let's just quickly write this out. And in the first one of 2, we're bringing in 1 0 from the right, and now we need to copy this number out, making sure we keep it diagonal. So we're writing it out just shifted along by 1. And you can see here that I've brought across this 0, which has come from here, and it's now in, beyond this initial, 8 bits. And so in binary, leading zeros don't matter, so we could get rid of these, but it demonstrates what's going on. And now the next one, so the second of these 2, we need to add another 0. We've got our original 0 from the first one, and we need to do the same idea. So this line here is our answer. We could just, as I say, ignore these leading zeros, because like in denary, 0, 5, 1 is 51, so we don't need this leading 0. So we could just write out 1, 1, 0, 0, 0. These ones do matter, and because this could be 11,000, we can do the little suffix to show this is in binary. So that's our answer. The main thing is to concentrate when we're doing this little shift, because it's easy to mess up, especially if there are kind of ones interspersed. So we're told that the arithmetic effect of applying a left binary shift of 1 to a binary number is to multiply it by 2. So every left shift we're timesing by 2. So it means to state the effect of applying a left binary shift of 3 to a binary number. So each shift is times 2, and we're doing 3 of these. So 2 times 2 times 2 is 8. So we're going times 8. And the general formula for this is it's times 2 times how many shifts you're doing. So n shifts. So if it was 5 shifts, it's 2 to the power 5. And a right shift is doing the opposite, so it's dividing. So if this was a right shift of 3, it would be going, okay, we're dividing by 8. But that's not part of this question. So actually the next question does use that idea. So what will the effect be of a left binary shift of 4? And then, so let's just do left, which is times 4, so times 2 to the 4. And the right by shifting it by 5. So this is now divide 2 to the 5. Well, you don't have to actually execute these or evaluate them. You can just go, okay, well, we're timesing it by 4 and then dividing by 5 in terms of the powers. So this is just, they cancel each other out. The powers of 4 cancel each other out. So we can just go, okay, well, we're going 2 to the power 0 divided by 2 to the power 1. So we're dividing by 2. Just for the avoidance of doubt, the reason why the base is 2 in all of these cases is because we're dealing in binary. If it was in base 10, the base would be base 10, and in hexadecimal it would be base 16. But the same idea applies, it's just they're used a lot more in binary because timesing by 2 is a really useful operation in lots of programming tasks. Question 4 begins with a sound engineer recording a singer. We need to describe why the sound must be converted to a digital format before it can be stored on a computer system, just for 2 marks. So this is all about the fact that sound is stored as sound is a wave, so that's how sound's created, by creating waves. And this is analog. So most things in nature are analog, as in they have a continuous range of values. So we can look at this at any point and get a really specific value for amplitude in this case. But actually computers can't deal with this. They have to stick to a set of discrete values, which is what digital is. So digital being binary, analog being what happens in the real world. We need to somehow convert it to digital to be able to work on or to be able to be stored in this case on the system. So let's say that sound is analog because it has a continuous range of values. That's 1 mark, and then we can say whereas a computer requires discrete values. And then we can say e.g. in binary because that's how it usually is. And that gives us our 2 marks. We could also say something about having to convert between them, but I think that's in the question, so that's implied. To do this conversion, we need to do something called sampling, and now we have a sound engineer using a sampling rate of 2000 Hz and a sample resolution of 4 bits. We need to give the answer of the minimum file size of a 5-second recording, and it should be given in bytes for 4 marks here. So we've got various steps involved here. So first of all, let's talk about what a sample is. So let me redraw that wave I did. So what we're doing when we're taking a sample is at set intervals, we are pausing and basically recording the value, and in this case it's the amplitude. So how many times per second, if this axis is time, is our sampling rate. The unit hertz is samples per second, that's what hertz is. And the sample resolution is how many bits we are assigning to this value, and in this case it's 4 bits. So that doesn't make sense, it'll be the other way around, but the actual sample itself is 4 bits in this case, and we're doing this 2000 times per second. So if we're doing 2000 samples per second, therefore 5 seconds is going to be 2000 times 5, which is 10,000. So 10,000 samples are being taken. That looks like an S, but that's meant to be a 5. And then each of these samples has 4 bits assigned to it. That's what the resolution is. So 10,000 times 4 is 40,000. I said the maths wouldn't be massively difficult. So this is how many bits. So that's actually how many, that's in terms of bits, because for resolutions in terms of bits, but we have to give it in terms of bytes. Well, there are 8 bits in 1 byte. So we need to divide this by 8, which gives us 5,000. So 5,000 bytes is our answer here. And this is the minimum. We'll also have mesh data as well, so this won't be the absolute size of this file, but it cannot be any smaller because of these conditions which have been enforced by the sound engineer. So just to recap, the sampling rate is how many samples we're taking per second, and the sample resolution is how many bits are assigned to each of those samples. And because of the sampling rate is in terms of 1 second, we have to scale it up to whatever the length of the recording is, which is why we're multiplying it by 5 to get to 10,000. So more formulaically, the size in bits is going to equal the rate times the resolution times the length in seconds. And this question is just asking you basically to evaluate these, so not massively difficult, and then do a little conversion at the end. But a harder version of this, or slightly harder, could be having to rearrange this a little bit. So maybe rate is missing, but you have all the other values, so you have to do a tiny bit of algebraic rearranging. Again, that shouldn't be too difficult, but it's not always going to be in this exact format, but it's always going to rely roughly on this equation. So we've been told already that the sound engineer currently uses a sample resolution of 4 bits, which it tells us now enables a sample to be stored as one of 16 different bit patterns. And she wants to increase the number of bit patterns available from 16 to 32, and we need to give the answer which shows the minimum sample resolution she can choose, which will allow her to increase it to 32. So let's take a step back and say, well, sample resolution of 4 bits gives us 16 because 2 to the power of 4 is 16. So that's how we work at combinations. Our base is 2 because it's binary, and 4 is how many bits we have available, which gives us 16 combinations. So quite simply, we're trying to get this to be 32. Well, what's the missing value? It's double this, which is going to give this 2 to the power 5. So 5 is our key value here, and we have it listed here as an answer, which is always a good sign. So that's the answer for this question. Right now we need to shade the lozenge to show which of the following statements correctly states the effect of increasing the sampling rate. So let's draw this graph for a third time. So if we're doing a sample, let's say this is 1 second and we're doing a sample twice, we basically are getting these 2 values back from the real sound. So we're basically representing this as like a straight line down. So it completely misses all of the added complexity of this. So clearly the sampling rate is far too low, but if we do this much more frequently, we start to get the true picture of this sound. Even if it's not perfect, we're still missing off bits. It's much more accurate than just taking a sample at too slow a rate. So basically, you improve the quality because it becomes more true to the original, but the file size gets far bigger because we have to include all of these values stored in our file, whereas before we're just including 2 values in our file, but now we've got way more. So it improves the quality and increases the file size. Right, now we have the first of possibly several write an algorithm questions, which some people love, some people hate. If you do hate it, I have got a video which talks about how you can approach these questions, so that may help. A link will be in the description. Also, it says here you can use either pseudocode or a flowchart. I would always recommend using pseudocode if you can, and I have a video on that as well, so that will also be linked. But anyway, in this particular example, we've got the subroutine char to code, and it takes a character as a parameter, and it returns the integer ASCII value of a character, and it gives us some examples here. So we supply the character and it returns the value according to the ASCII character set. So we need to develop an algorithm to ask the user to enter a character, output lower if it's a lowercase character, and output not lower if it's any other character. And we must use this built-in subroutine in our answer. For 7 marks, so a lot of marks for what seems on first look like not a very long algorithm, but let's see how this goes. First things first though, let's just do the basic thing and do the first bullet point. So they always pretty much always give us bullet points, which usually separate out our problem quite nicely. So first of all, let's ask the user to enter a character. So the way I would do this, well, this kind of standard way is just to name our variable first of all. So let's just call this character, shall we? And I do my variables with an equal sign. AQA do that little arrow. You can do it how you want. So character equals, and I always do like capital input, and let's just say enter a character. So in my head, this is like a built-in function that asks for the input. I'm supplying this string as a parameter to print out to the user this statement, and then they type it in and it gets saved as this character. How you do this line is up to you. Different programming languages deal with input differently. I think this is kind of based on the Python way of doing things, but you can write this how you want essentially, but we're trying to save this so we can use it later. And now we need to do a bit of logic where we have to output lower if it's a lowercase character and not lower if it's any other character. So the way we're going to do this is by using the ASCII numbers. We can't just we're not going to have 200 if statements for every single character. We need to use the numbers to do the next 2 bullet points. So first of all, we need to actually use this function, this subroutine, to get the character code. So this does all the hard work for us. So let's get that by saving it to another variable. So let's call this one, let's just make it a bit shorter, char code. And now we need to call this subroutine using our character as the parameter or the argument. So we need to call it like I have with the input built-in function. So char to code, and we need to supply our input so we get its value. Alright, so if the user had entered A, like in the example up here, 97 will get saved under this variable, and this isn't meant to be a gap, that's meant to be all one word. Anyway, so how do we decide if this character is lowercase or uppercase? Well, fortunately their example does this, or tells us how to do this essentially, because it shows us, for example, for both A and Z. So these are all lowercase, and ASCII is the codes are consecutive, so B is 98, C is 99, etc. all the way up to Z, which is 122. So all the lowercase characters are in a row, and every other character outside of this range is going to be not lower, i.e. everything else. So all we need to do is basically check to see if this character code we've already got saved is within this range 97 to 122. And we're going to do this using an if statement. So that's our selection block. So I always capitalize it. So if char code is let's do the lower bound first. So is greater than or equal to 97, I believe. And we could have done this a little bit better, but let's just use binary and, because we need to also check that it's below the upper limit as well. So let's do this on, we can do it on one line. So in this case it needs to be less than or equal to 122. It says output, but you could do print, and we're going to do lower. Make sure it's in quotes because it's a string, or let's do it uppercase as they say. So a string in uppercase. And again, how you do the output and the if statement is sort of up to you, but you can see it's really important first of all to make sure we have greater than or and equal to. We could also do greater than 76 or less than 123, same thing. And shows that it's got to be both right? If it was just one of these, if it was above 122, then it would still print out lower, even if that's not valid according to ASCII. So it's important we have both bounds of this range. And now we can just do else to cover all other cases where we're going to output not lower. And I like to close off my if blocks, my selection blocks, with end if, and also note that I've done indentation here. I think it makes it look a little bit nicer, even if it still looks quite messy. But that's it. So a really easy 7 marks. And this just shows that often you get marks just for doing really basic stuff. So having an input statement, having a variable, having your strings in quote marks, having an if statement, having some conditions. So you basically get marks for the really basic things in programming, which hopefully all of you are comfortable with. So some people, I feel like this is this isn't the most difficult one, but even if this was a really difficult problem, you still get quite a few marks for doing the basic stuff that are in this question as well. So make sure you always try these out. Even if there's one part of this type of question which you can't answer, you can still get almost all the marks by doing just the basic things right. We're now shown another algorithm, and you can see how their pseudocode is similar to mine in some ways but different to mine in other ways. They also capitalise for keywords and indent as they're going along the nesting. They also do things like then and close off the blocks, but they do the arrow for variables, which I don't receive a point of personally, but it doesn't matter. Pseudocode, as long as we understand it, is perfectly fine. Doesn't matter how you do it. Anyway, so we have this code which is for a sorting algorithm, and the indexing starts at 0, as it often does. And first of all, we need to state the data type of the variable sorted up here. So sorted, first of all, is being initialized to false. Well, false, and then it goes to true. So we only have 2 values here. That means it's Boolean. If it was false in quotes, it could be a string, but we're only going one of 2 values here, true or false. That's what Boolean is. And this identifier, this variable, is used in the algorithm above. Explain why sorted as an identifier is a better choice than using the identifier s. So an identifier is the name part of a variable, a array, a subroutine, a constant. So whenever we give something a name, that's what its identifier is, the name part of it. And for a computer, it doesn't matter what the name is. As soon as you compile this or run it, the names get rid of, they get replaced by a number for the computer to use. But they're useful for us. When we look at the source code, we can see what's going on if we bother to give them nice descriptive names. So in this case, sorted, the name tells us, the identifier tells us its purpose, whereas s on its own does not. And let's say this makes the code more readable. So readability is about how easily you can understand the code by looking at it. Now we need to shade the lozenge to show which of the following contains the full statement about this algorithm. So first of all, does it use a named constant? Does it use indefinite iteration? And finally, does it use nested iteration? So let's go back and have a look and try and remember those 3. So first of which is a constant. So let's look for a constant. A constant is a variable which cannot change, and often we have, this isn't implicit. We have to say something like, okay, the constant is going to be pi. So we've actually got to use a keyword to tell the compiler that it's going to be kept constant. Otherwise, it will just default to being a variable where it can be changed. So it doesn't have any indication that there's a constant. So that suggests to me that that is going to be the full statement. But let's just look at the other 2 first of all. So what was the other one? So indefinite iteration. This is where we don't know how many times it's going to iterate just by looking at the loop. So basically a while loop is indefinite iteration, which we have here. A for loop is definite iteration because in the definition of the loop, in a for loop we're saying something like for I in range 1 to 5. So we know the range, whereas here, looking at it, we can't tell. We have to look at the rest of the code. So we have got that, so that's true. Also, we were talking about nested iteration. So nesting is where we embed control structures within a wider control structure. So here we've got a while loop here within a wider while loop. So this is a nested while loop, the one in the middle. So we have got that. So it's for constant, which is false. So now we've got a 6-mark trace table question, and I've copied the algorithm down here so we don't have to keep going back and forth. And that's important because we're really needing to go through this step by step to fill in the values of our array and also our variables here. That's what a trace table is for. It keeps track of our values as execution moves forward. And this would be So the real life application of this is in testing, mostly to find what we call logic errors. So I'm pretty sure I mentioned these in passing earlier. So these are errors which don't cause your code not to run, so your code works, but not in the way you intended. So something is going wrong, some of your values are going a bit funny, and maybe you're not quite sure why. So you do a trace table to see where they suddenly change to the wrong value, essentially. So they are really useful, but they can be a pain to do in exams because you've really got to concentrate and see what's going on. So let's see how this one goes. We're keeping track of our array and also 3 variables here. And you can see the first line is just the values that are here in the initialization step. So we're initializing our array to 4, 1 and 6, and we're setting sorted to false. So that's what this first line does. I and T aren't really involved at this point. So one key issue for students is where you leave gaps in trace tables. Some people think you have to fill in every single box, and you don't. So there's going to be quite a lot of white space in this kind of table structure, and that's perfectly fine. The way examiners mark it is basically just by looking down the columns. So they'll check that your columns are in the correct order. So you've got 4, 1 and 5, 1, 2, 5, whatever it is. They'll check for the order. They don't really care about where the gaps are in most cases. But I'll talk you through this as we go along. So, so we need to start by going while sorted equals false. Well, it does. We're going to set sorted to true. So what you need to do this on a second line because you've already filled in that gap. But anyway, this is like a second stage of the program. So I is set to 0. And you could put it up here, but again, it just makes sense to keep things roughly together where they are in the program. Ultimately, as I say, in real life, you'd be using this to help yourself out. So you want to keep things as logical as possible. So now we're going, while I is less than 2, well it is because it's 0, we're going to evaluate if array and I plus 1 is 1. So if the first value in this array, which is 1, is less than the 0th value, which is 4, then we're going to continue. Well, 1 is less than 4, so we do execute this if statement, or this if construct I should say, and now we're setting t to being the 0th value of this array. So that's our next step. So the 0th value is 4, so t becomes 4, and I'm doing this on a separate line because it's like a separate construct. Then the 0th value in the array is now reset to be the first value, so what is currently 4 becomes 1, and then what is currently, and then the first value becomes t. So what is now 1 becomes 4. So maybe let's do this actually on the next line to separate things out a little bit. So what we're doing really here is t is our temporary value. We're swapping these 2 values in the array to try and sort it. That's what the purpose of this is. And we can't just swap them. That doesn't work in programming. We've actually got to use a temporary variable to keep track of it so we don't lose it. But that's not the end of this. We then have to set sorted back to being false. So that goes back to false. And that ends our if statement. And we set I to I plus 1. We increase it by 1. So 0 plus 1 is 1. Do it outside of that if block. And now we'll go back to this nested while to see if it's still less than 2. Well, 1 is less than 2, so we keep going. So if so I is now 1. You've got to concentrate for this. So 1 plus 1 is 2. So now we're looking at let's say the second value in the array according to the index, which is 6. If that's less than the first value, if that's less than if that's less than the first value, which is 4, then we can continue. Or 6 is greater than 4, so fortunately we can this time skip this body, and we have to set I to I plus 1, so this now becomes 2. And I is less than 2, well it's not because it's 2, so we can skip this and go back to the wider while loop. So while sorted equals false, well it does. Unfortunately we've got to go through this process again. So now we reset sorted to true and set I to be 0 again. And now if the first item in the array is less than the 0th item, so the 0th item is 1 and 4 is our first, well 4 is bigger than 1, so actually we can skip this whole bit and skip to I equals I plus 1. Well 0 plus 1 is 1, and we need to go back up again. So why? Because while I is less than 2 and it's 1 currently, but nothing's changed here, so this condition is still going to get not met. So now we just set I to be I plus 1 again. So 1 plus 1 is 2, and the condition is now broken. So this is it. That was fairly heavy. This is not the easiest example, I have to say. In some cases, this will be an easy 6 marks. In this case, you've really got to concentrate, and it becomes a little bit more confusing because we have zero indexing. So we're talking about the 0th and the 1st and the 2nd item. So a little bit confusing, but you can see hopefully how I've done the line breaks. I've tried to kind of separate things as best I can. Hopefully, if you were to follow this again by pausing the video, you'd see, how these numbers relate to each other. And like I say, the examiner is all they're going to do is just look down the column to make sure you've got the values which match up with their mark scheme. They don't particularly care where these gaps are. When you have nested structures like this, you really got to make sure you finish those structures before you move back to look at the wider one. So for example here, you've got to really make sure this while loop or this nested while loop is complete before you go back to the start to look at these other conditions. Next up, we've got to fill in the values in boxes to show how the merge part of the merge sort algorithm operates. And this code we just looked at, this pseudocode, is actually for bubble sort, as some of you may have noticed. So it's moving along the list, swapping them if they're out of order, and eventually they end up sorted, so 1, 4 and 6. So that's what this code is doing, bubble sort. But now we've actually got to show merge sort being used, and the actual code for merge sort is more difficult from bubble sort because it uses a concept which we don't learn at GCSE called recursion. So merge sort works by first of all dividing the list up into individual parts. So it's basically skipped the first bit, the divide step. It's just showing us the merge step here. But first of all, it just basically continually divides the list until each sublist is only of one item long, so just one item on its own. So it skipped that step, but the merge step is where we actually start to put it in order. So we're putting it in ascending order here. And the first thing it does is look at two sublists together. So 7 and 3. Well, 3 is less than 7, so it will rearrange them. And now 4 and 1 is less than 4, so it swaps them. 2 and 8 are fine, we just put them together. And 5 and 6 are fine as well. So we're starting to combine them. And it does this always by doubling. So now we're putting two lists together. So we have to order this kind of ourselves, right? So 1, 3, 4 and 7 is the correct order if we put this list together. And the whole point of sorting, well obviously the whole point of sorting is to put it in order, but the whole point of putting this in a very formal algorithm is so that a computer can do it. We can just look at this list and put it in order ourselves because we're smart enough to do that, but a computer needs to follow these really strict instructions to do this. And this step here, where we start to kind of jumble up sublists, or essentially we're starting to order this ourselves without using this algorithm. And the reason why we have to do this in merge sort is because it uses this concept which is above GCSE level. So once you understand a bit more about how this would be implemented, this step seems a bit more, it seems to make a bit more sense. At the moment it seems like a bit of a jump. You're starting to suddenly order it yourselves, not following this algorithm. But this is part of the algorithm, it just uses something called recursion in actual use. So anyway, that's fine, maybe I overcomplicated that. In here we have two, let's go back to green. We have 2, 5 and 6 and 8. And then we end up with our list put together. So there you go. Now I need to state one advantage of merge sort compared to the sorting algorithm in figure 2, which as I said was bubble sort. And this is not totally easy to do because a bit like up here when I was trying to do the implementation, it's a bit above GCSE level. So we start to actually, at A level and a university in particular, start to actually formalise this using maths. But essentially, merge sort is more efficient. So really, we're trying to say it's quicker, especially over. So that's probably sufficient, but we could also just quantify it by saying especially over large lists. So if you want to know the mathematical equation, we use something called big O notation to show this. So in the average case, bubble sort takes n squared steps, whereas merge sort takes n log n steps. So on a graph, the graphs actually look fairly similar, but it does become more pronounced over time. So a quadratic graph is something like that, right? Whereas an n log n graph is a little bit less steep and is kind of slightly better. So if this x-axis is the input size, that's what n is, so how big this list is. So this list could be 1,000,000 items long. and then the y-axis is like time or work or how many steps, that sort of thing. You can see that actually at the same n, it takes bubble sort a bit longer than it does for merge sort. At small inputs, when the lists are very small, the difference is not going to be huge, but over time it does become quite significant. So merge sort is about as good as we can get. Bubble sort is really not very good. Now a programmer implementing the algorithm in figure 2, the bubble sort one, decided to create it as a subroutine. They removed line 1 and the array was made a parameter of the subroutine. So let's have a look at what they mean by this. So they're getting rid of this array and they're making this a subroutine, so it'd be something like not binary, bubble sort, and passing in the array instead of having this line here. So that means, so at the moment this array here is hard coded, so it's only ever going to use 4, 1 and 6 to do this sorting, but actually it's not very useful that way. We want to be able to pass in any array to do this. I mean, it does actually hard code the length here, so you'd want to change that code, but essentially we can pass in any values and it will sort it for us, not just these ones hard coded here. And that's one of the key advantages to subroutines. They can be reused as many times as you want. So let's first of all say it can be reused without repeating code. Instead of having to copy the entire block, we can just define the block once and then we can call it with just one line whenever we want to, and it saves us repeating that code. So that's a huge advantage. But also what I was trying to say about we can it becomes more general. We can any array can be used, not just the hard-coded one. Other reasons include testing. It's easier to test your code and find errors if you have less repeated code. Also, things like abstraction. You don't have to understand what's going on inside the subroutine. All you have to do is understand its input and its output. So you know you're going to pass in an array and you're going to get out a sorted array. You don't particularly care what sorting method it uses, whether it uses merge sort or bubble sort. You don't particularly care. So that's removing some complexity from your problem. Right, we've got another develop an algorithm question here, and again we can use either pseudocode or a flowchart. I would strongly recommend pseudocode, but it's up to you ultimately. So here we're allowing a taxi company to calculate how much a fare should be. So it should, first of all, prompt the user to enter the journey distance in kilometers, and it must be greater than 0, and they should be made to re-enter it until the distance is valid. So we have some validation here. We also need to prompt the user to enter the number of passengers, but no validation is required for that. So we have two separate inputs, but we have to do some validation for the first one. And then we actually do the calculation. So we charge £2 for every passenger regardless of the distance, and charge a further £1.50 for every kilometre regardless of how many passengers there are. So two kind of separate steps here which combine to become this final taxi fare. Quite a few steps here, but there's no, to my first impression, any difficult logic within this. So you sort of just have to follow this line by line. So first of all, let's do, similar to earlier, a variable where we take the input distance. So let's just do a distance variable and set this to be a user input where we ask them to enter the distance. But we can't leave it at that. We can't just allow any input. We've got to make sure that it's greater than 0. And the way you do this, and the clue is in the second bullet point here, we can't just go if distance is less than 0, ask again, because it's got to be this infinite loop. They could get it wrong a million times and we still need to ask them again from one time. So we need to do this with a while loop, essentially. The reason why we can't do a for loop is because a for loop is definite iteration. Here we don't know how many times the user is going to mess up, so we need to do a while loop. So while distance is less than 0, is that what it says? So while distance, yes, it's going to be greater than 0. Okay, so less than or equal to, like that. We need to, let's do then, we're going to ask them for it again. And we just need to repeat this line essentially. Okay, we can just add a little note saying, you know, what's wrong with it. So it could be 0.1, 0.1's fine, but 0 is not allowed, which is why we've got less than or equal to here. We could do less than sign with an equal sign next to it, but because this is pseudocode, that's okay as well. So this will just keep repeating until it gets a correct input. So let's just close off this while loop, and that's just generally how you do this kind of validation. So if it's a different kind of question, that's just how you would do it. So we can now move on to our next input, which is more straightforward. We don't have to validate this. So let's just do number of passengers. Do it in a different color. So passengers, it's a very similar line. So enter the number of passengers. And now let's do this calculation. So maybe, well, we could just do this in one line, I suppose. So well, let's do it in 2 lines, because let's do actual variable for the fare. So let's say fare equals, and then what is this calculation? So we're saying we want £2 for every passenger. So let's do that. So first of all, we're doing, so let's do 2 times passengers plus, what is it for distance? It's £1.50 for every kilometre regardless of how many passengers. So this is like a separate clause. So £1.50, 1.5 times distance. And now we need to actually output this. So let's just say output fare. And that gives us our answer. So again, it's 8 marks, which my impression is that this is quite a generous 8 marks. Maybe you disagree, which is fine. But that's for basic process. The main bit here, or the main bit that's different to other questions, is validation. But again, it's going to be the same regardless of kind of the condition that's being validated. Question 8 gives us a truth table for the AND logic gate, and we have to complete it. So truth tables are there to show us all possible combinations for a logic operator. Here we've got AND. So AND is Boolean, which is why we've only got 0s and 1s, true or false. So AND is only returning true or only returning 1 if both inputs are true or both inputs are 1. So it's going to be 0 in all cases except when both inputs are 1. That's just what the AND gate does. Next, we're told that a logic circuit is being developed for an audio advert in a shop which plays automatically if a customer is detected nearby. So it's got 2 sensors, A1 and A2, which detect if a customer is near, and it plays if either of these sensors are activated. So it should only play if another audio system S is not playing, and the output is Q. So, well, the output Q being it's either going to play or not play, so it's either true or it's false. So I need to complete this logic circuit for the system, and basically what it's asking us to draw here is logic gates. So the 3 logic gates are, let's just do it because we've got empty space here. We've got AND, which is like this, not very good. 2 inputs and 1 output. We've got OR, so that's AND. We've got OR, which is a bit more like a crescent moon shaped thing. Again, 2 inputs, 1 output. And we've got NOT, which is this. So 1 input, 1 output is just doing the opposite. So we're going to be using those in this. Which ones exactly? We need to go back and have a little think. So 2 sensors, A1 and A2, which detect if a customer is near. And the key word is in the second sentence, which says the audio plays if either of the sensors are activated. So either is where OR comes into it. So OR will be true if either of the inputs is true. So the OR one is 1, 1, 1 and 0, 4 when both are 0. So we need to use OR somewhere. So where are we going to use OR? We're going to use OR for A1 and A2. Those are the 2 inputs for 2 sensors. So let's draw the OR. Oh, that's not good. The OR diagram there. Yeah, that's really not good at all. But we've got our 2 inputs fed into this, and we've got the output. What happens to the output? We don't know yet. So it's only going to play, this is only going to return true, Q, if another audio system is not playing. So we need, so S will be true if it is playing, and we want it to be not playing. So we need to use the NOT gate here. Let's do a different colour. So NOT, as I said, is the kind of triangle with a little dot at the end. And we have the 1 input fed in. I've gone a bit over there. 1 input fed in, and then for 1 output coming out. And now we basically want both of these things to be true. We want either sensor to be activated, and we also want this to not be playing. So the way we combine these to get an output is with AND. We basically need both conditions to be met, which is why we need our final gate. So this is nice because it allows us to use all of our logic gates. and they're kind of joined together by and, like that. We basically have two branches which we need to be true for this output to be true, i.e. we play this advert. So either sensor needs to be true, so we get a 1 here, and this needs to be, well, it starts off as a 0 and then it becomes a 1, and we can combine them to get Q. So that's how it works. This is a fairly standard question, I have to say. The circuit almost always looks a bit like this, because this is a very, very common scenario, just not with these specific examples. If your pictures aren't very good like mine, you might just want to actually write in the gate what they are, just to make it a bit clearer, because that's not a very convincing back of the OR gate. Question 9 begins talking about subroutines again. So the fact that subroutines are here in this paper so much really reflects how important they are to modern programming. So these subroutines control the way that label blocks are placed in different columns. So block on top takes the column and returns the label of the block on top of this column. Moves a block on top of the source column to the top of the destination column, and height returns the number of blocks in the column which is supplied as a argument. So we're given how blocks A, B and C are arranged at the start of this, so CBA from top to bottom, and we need to draw the final arrangement of the blocks after this following algorithm is run, just using the move subroutine 3 times. So let's just go back to what move does, because I wasn't really concentrating. So we're moving the block on top of the source column to the top of the destination column. Okay, so move 0, 1. So we're going from column 1 to column, sorry, we're going from column 0 to column 1. So C is at the top, so it goes to column 1. So this is our final output. So let's just maybe do it up here. So C is now there. We then are moving B to 2, and then moving A to 2, like that. So we now end up with no blocks on column 0, 1 on column 1, which is C, and then B and A on column 2. And we get 3 marks for that, somewhat unbelievably. And we've got another 3 marker here with a very similar looking question. So same arrangement at the start, and we have another algorithm. So while the height of column 0 is greater than 1, so it's currently at the start a height of 3. So this is true. We move 0 to 1. So sorry, we move from 0 to column 1, which is the top one. So C goes to here. It's taken off the top. The height is now 2 because C is gone. It's still greater than 1, so we move B to column 1 because that's the new top. So it's gone now. Now the height is 1, so we don't loop because 1 is not greater than 1. So we move the top one from 1 to 2. So B is now at column 2. So A is still here, C is in the middle, and B is in column 2. So let's do that. Right, now we have another version of the same kind of question, just with a slightly harder looking algorithm this time. So we're increasing difficulty, it seems. And this is using the modulo operator, or modulus, or just mod. And it does helpfully explain what this does, although you should know it just anyway. So the mod operator calculates the remainder resulting from integer division. So for example, 13 mod 5 is 3, because 5 goes into 13 2 times, 2 whole times, which is what integer division is, 2 whole times, which gives us 10, and then we find the difference between 10 and our original value. So 13 minus 10 is 3, which is why we get that input. And that's important here. So first of all, let's just trace through this again. It's very much like the trace table question, just checking how much you can follow. So we've got a for loop. We start off with C being equal to 0, and we keep going until it's 2. So first of all, if the block on top of column 0 is B, then we do this, but it's not, it's C, so we go to else. We're going to move from column 0 to this value here, which we need to evaluate. So C is 0, plus 2 is 2, so 2 mod 3 is what we're evaluating here. And this is a little bit different because we have our second value bigger than our first value. So integer division is also written as div like that. So 2 divided by 3 is what, 0.66 in what we'd call real division, recurring. But 2 integer division 3 is 0 because 3 doesn't go into 2 at all. You know, it's only a partial, which is why we get a decimal less than 1. So we're trying to find the remainder here, And we basically copy what we did here. So we're going, okay, well, we've got 0 as our answer. So what's the difference between our operand 2 and our result 0? Well, it's 2. So the answer here is 2, or sorry, what it evaluates to is 2. So we're basically going from column 0 to column 2 here, and we're moving for one on top, which is C. So C is now over here on column 2. It's removed from column 0. So C, it's a bit confusing because we've got a variable called C and a block called C. But the variable called C, because we've now ended our for loop, is increased to 1. So C up here is now 1. And now if the block on top is B, well it is, so that's good. We can now execute this statement. So C plus 1, so 1 plus 1 is 2 mod 3. We've just done that, which gives us 2. So we're moving from column 0 to column 2 again. In this case it's B that's getting moved across. So B is joining C over here. We now go back to the top. Well, C is now 2, so we have a final execution to do. Once it becomes 3, we end the loop. So now if block on top is B, well it's not, it's A. So we now need to move 0, and 2 plus 2 is 4. So we're now doing 4 mod 3. This is a little bit easier because 3 goes into 4 once, remainder 1. So the answer is 1 here. So A goes from column 0 to column 1. And that gives us, that's it, because as I say, we're now beyond this range defined by the for loop. So A is gone from here, but let's copy this down to the actual answer. So you just got to be a little bit careful. It is a little bit, well, it doesn't necessarily make sense when we're dealing with ones like 2 mod 3. You just got to make sure you follow the pattern and you'll get the right answer. Right, now we've got another developing algorithm question, which is actually on this case study, which makes things a little bit more interesting, at least for me, because I do tons of the other ones all the time, but this is a little bit different. So we're trying to move every block from column 0 to column 1 here, and it should work however many blocks start in column 0. Okay, not sure what that means or if it even makes sense. You may assume there'll always be at least one block in column 0 at the start and the other columns are empty, and the order of the blocks must be preserved. So we need to use the move subroutine to actually move them from one column to another, so we can't define our own one. We've got to use the one they have defined for us, and we should, it says should, also use the height subroutine in our answer. So for example, we started with B and A and we're trying to move it to column 1 in that order. So the issue straight away, it's only for 5 marks by the way, so the issue straight away is surrounding this point here, in fact the order must be preserved. So what move does, as we've seen in the previous sort of 3 questions, is take the one at the top and put it at the bottom. So if we were just to do the simple naive, well, we're going to move B to column 1, then we're going to move A to column 1. We'd end up with A and B, which doesn't match their example. The order has got to be preserved as we do this. And the answer I imagine, on first impression, is to do a little bit similar to how we did earlier with the bubble sort algorithm, where it uses a temporary variable to kind of hold the swap. So what we can do, we can effectively use column 2 as our temporary variable. So if we move, first of all, B into column 2, I don't know why I did the arrow, we can then move A into column 1, and then move B back into column 1 like that. So that's how we can preserve the order. We have to make use of this essentially temporary variable if this was an actual programming problem, which is going to be as we do this, I think. So let's try and implement this kind of 2-stage solution. So how are we going to use height? That's another question. This line here, your algorithm should work however many blocks start in column 0, I think is trying to say we need this to work regardless of the size of this column. So we want to make this nice and general, so that however big this is, as long as it's got at least 1, we can do this process and it will work. So actually we want to do something a little bit different to what I said. We're first of all trying to move them all over into column 2 and then move them back into column 1. So not go straight from column 0 to column 1. We want to do it all into column 2 and then back into column 1. So this is actually mimicking something you'll learn at A level, so we won't go into that right now. But first of all, we need to use a while loop. So let's do while height of column 0 is greater than 0, because we're basically going to finish once column 0 becomes empty, as they've all moved into column 1. So that's our kind of overriding while loop. We're we're going to move, so while the height is greater than 0, each time we're going to move the current top value over into column 2 as our kind of temporary stack, which is the A-level concept I was mentioning. So going from 0 to 2, and we can end that while loop, because that's kind of like our first stage, is to get all of them over into column 2. Now we need to actually move them to column 1. So it's basically the exact same code just for column 2 in this case. Of 2 is greater than 0. We need to move them from 2 over into 1, and then the order will be preserved from the first step. And that gives us our answer. So basically 2 move operations, which are nice and general, so we're not just hard coding it for when we only have 2 items. This will work as long as we have our first item, we have 1 block, this will work. So it'll keep going, this move operation, until the relevant column is empty, and then it will move on to the other side of this process, going from 2 back into 1. So hopefully you can see how we're using this temporary, stack, this temporary column to be able to preserve the order, because otherwise the order is not going to be kept consistent. We have another subroutine, so these questions are very repetitive, which is good actually. So this one is used to authenticate a username and a password, and again the indexing starts at 0. So we need to deja vu, complete the trace table for the following subroutine call. So when we have Alice as our username and woof 2006 as our password. So it's a simpler version of the one we did earlier. So Z and correct are our 2 variables we're keeping track of here. So we start off, so when we call this, right, we're basically jumping. So a subroutine, I should have said probably right at the start when it was first mentioned, is this out of line block of code. So this is our definition of our subroutine. This is usually done right at the top, maybe in like a separate file, and then we reference it. Our calling statement is done in our main body of code. So we basically will jump the execution. Once this line is run, it jumps back and runs this code using these 2 arguments. So Alice and the password are the 2 arguments. So first of all, we have US and PS, the list of usernames and passwords presumably, but we don't care about them for our trace table in this case. So we're looking for Z. Well, Z starts off being assigned 0, and correct starts being assigned false. And then while Z is less than 3, we check to see if this username, Alice, equals the index of Z, which is 0 here. So does user equals the index of Z? No, it doesn't. Dave is not Alice. So we skip that one and increment Z. So Z now becomes 1. And we go back because Z is still less than 3. So now we look at the first index, which is Alice. So they do match up. And then we look to see if the passwords match up. So does password equal the first index of password? Yes, it does. So correct becomes true. And then Z is incremented. So Z becomes 2, because even though we've kind of got the result we want, we still need to follow this code, right? So now Z is still less than 3. And now this isn't correct because we're looking at Bob and this password. So we still need to increment it. So now this becomes 3, and the loop is broken because it now doesn't meet the condition, and we can return correct, and this is our answer. So really simple actually. It's really testing you to see if you're going to keep going once you get to correct. You can't just suddenly jump to the return value. You've got to keep going throughout the whole loop, even if you're even if you know the answer already, you've matched up the passwords and the usernames. For the next question, we have to state the value which is returned by the following subroutine call. So Bob is our username here, and ABF32 is our password. So let's see if this just matches up in the list. So it doesn't. Dave is assigned to ABF32, so if it doesn't match up, we would end up with false being our output here, because it doesn't match up. So false is our output from this subroutine. Okay, for the final 2 questions of this exam paper, I've copied it down just so we can see a bit more easily. So line 7 and 8 here and here, so if and here could be replaced by a single line, and we need to show which one would be the correct one. So we're essentially doing an if statement saying if the username equals the username of the index in the list, then also if the password. So basically we're looking for both of these conditions to be true, and as we saw in the logic gate question, and is what we want to use for that. So it's going to be as long as we just check if this is correct, yeah, it's going to be B. And now for our final question. Tragically, we have a programmer implementing this subroutine, and he replaces line 9 with return true, so over here, and line 14 with return false. So why is this now more efficient? Well, efficiency is in general about minimizing resource use, and we saw up in the trace table how when we managed to get Alice and Woof, we found a match out of these two lists, but we still had to keep going. It still loops another time to check Bob, even though we've already found the match. So it keeps going beyond what it needs to. And once we get to a return statement in a subroutine, it finishes execution. So if we had a return statement up here, right at the top, it'll finish straight away. It'll never run the code below it once it gets to a return statement, because we're done. That's what a subroutine does. It's there to return a value to us, or if it's a function in particular. So it makes it more efficient because it will exit as soon as it finds a match, instead of iterating over the entire list. So using multiple return values often saves us a bit of time, because we don't have to use Boolean values which only can be checked at the end. Okay, so that's it. Hopefully this walkthrough was useful. If you have any feedback or questions or comments or suggestions, please let me know. And apart from that, good luck.